and hello again everybody. We are going now to try and use matched filtering for our practical exercise number 3. I have already uploaded practical exercise 5 guidelines at Ortus. You can use them right now. And you will need the third practical exercise with manipulated signals, binary amplitude shift keying, binary phase shift keying, and so on. We have these files already prepared, but in case you missed that, well, you will be able to work on that later, because basically what we did in third exercise, we created modulated signals. In fourth exercise, we detected these signals by using correlator receiver. And in the fifth practical exercise, we are going to detect the very same signals with matched filter receiver, right? So let us begin. I'm going to start with amplitude shift keying and open the file where I have generated amplitude shift keying signal. Let's see if it works first. Okay. It's just thinking. Yes, it's working, right? The only thing is that I will remove noise for now, because we need first to make sure that everything is working correctly. So I'm setting signal to noise ratio to 100 decibel, which is equivalent to 10 at the degree of 10. This many times signal is stronger than noise. Well, actually, let me increase font a little bit for you, for it to be convenient, right? So I set this, and now I'm going to save the copy of the file as lab5 BASK. And I'm going, in similar way as in fourth practical exercise, continue this file. In fact, let me copy something from the fourth exercise, right? I'm going to take this. And here we will have matched filter receiver. Matched filter receiver. We will need this picture again, so we can keep that. Now that part we will change. So here we will make receiving. And somewhat this part will be still of use for us, so we are going to keep it for now. But we will need to edit it a little bit later. So now we need to implement the other type of receiver. So basically what's left is some plots of the results, right? So let's see guidelines, what we need to do. Basically, this is very same as the fourth practical exercise, but for other type of the receiver. The fourth was for correlator receiver, and the fifth is for matched filter receiver. So basically the entire process is the very same. We only need to change the receiver operation. But let's see again what you need to include in your report. So the objective of the practical exercise, which is here, the source code of simulation programs. There will be 3 programs for each modulation type, and the results of simulation. They are represented graphically for each modulation and noise on and off, right? So basically that would be 6 pictures, right? So amplitude shift keying, frequency shift keying, phase shift keying, with noise and without noise. 6 combinations. Now, what we need to do is to design the receiver with matched filters. The first step, as I have told you in the lecture, is to calculate the impulse response of our matched filter. So that's what we are going to do the first. We need impulse response of matched filter. For amplitude shift keying and phase shift keying, we are going to need only 1 filter, but for frequency shift keying, we will have to calculate 2 filters. That's because, well, actually there is only 1 carrier signal for amplitude and frequency shift keying, or phase shift keying, and 2 carrier signals for frequency shift keying. So this is our S0 carrier signal, which has been already prepared last times, and which is, well, actually, let me put a breakpoint maybe here, so that this program doesn't proceed further and tells that there are some errors because no sum of the parameters, right? So, and this S0 signal is actually these contents of the one symbol, right? So this is this harmonic signal part, and this one, and here is again 3 times in a row. So we need to actually have it inverted in time. So basically we need to flip. So this is going to be beginning of our signal, and this is going to be the end. For that purpose, as it has been shown in lecture, according to this formula, right, we need to calculate the impulse response. This impulse response can be done by simply flipping our signal. Now, in MATLAB Octave, there are 2 operations for flipping. Okay, I need to stop this program because it paused at this position. Now, basically, we can flip horizontally and we can flip vertically, right? So for horizontal flipping, we are going to use function flip left right. This is working only for vector row. And for vertical, we are going to use flip up down. So we need to know first if our signal S0 is a row or a column. So we can see here dimensions. And the first is the number of rows, and the second is the number of columns. So this means that actually S0 is a single row. Let's see if it's true by outputting it in command line, and we can see that actually it's in row. Now if we transpose it, that would become a column. So we need to use, in this case, flip left right, because it's horizontal signal, right? So let's do this. That would be our impulse response of the matched filter 1, flip left right of the signal S0. So we calculated this impulse response, and now we can perform optimum filtering. Now, there are 2 ways that we can do that. The first way is to use a filter function, and the second way is to use a conv function. Conv function calculates convolution. As you know, filter output signal is actually convolution of the input signal and impulse response. And filter uses transfer function, which is, for our case, polynomials of z. This is in Z transform, right? Where denominator polynomial is just 1. So basically, we are left with these coefficients represented by our impulse response HMF1. So these B coefficients are actually the very same impulse response, and the denominator here is 1. So basically, both of these functions work literally the same. They are both built-in functions, meaning that you don't need any packages for them to work. So it's really up to you to choose which one will you prefer. I'm going to show you both in order for you to see that they actually produce the very same result. But they are basically, well, they can be used both. The only difference is that actually conv calculates a little bit more data than filtering. It doesn't stop after signal ended, so we need to cut off the, well, let's say not excess data, but we need to cut off the data after the length of our signal, because there is more data than we need, and we don't need to take that into account. So Let's start with the command filter, since it doesn't need any additional operations and it's therefore simpler, right? So we are going just to copy this function actually, because, well, it's already prepared as we need. And here we are going to put additional command that we calculate output of matched filter. So that would be signal of matched filter 1. And now we are going to plot it here instead of as integrator. Now matched filter 1, and here we accordingly change the caption like first matched filter. Like this. Now we are going to suppress for now this and see how our signals look like if we did everything correctly. So yes, we did everything correctly, and now you can see that actually the picture is a little bit different than it was for correlator receiver. Let me remind you how was it looking for correlator receiver. For correlator, the only thing that I will remove noise. Receiver calculated this. Well, actually, now let me put here for now figure 3 so that we can see both of these pictures at the same time. And no. Figure 2. Wait a minute. Okay, so here we need to put figure 1 because it reused our second figure, which is not what we wanted. And now we need with correlator receiver. Here we have figure 1. And here we have figure 2. So basically now I'm going to run this file. This will generate me figure 1 and figure 2. This is going to update figure 1, which will be the same, and additionally generate figure 3. Now I'm just trying to show you these two plots at the same time. For correlation receiver to the left, to the right, and matched filter receiver to the left. Basically, as you can see, we have very similar pattern here. Here we have the very same triangular behavior. In some parts not. That you can see, for example, here we did not reset, right, and start over again, but instead we continue it. In correlator receiver, here we would have reset, and here we would have another reset. But basically, if we read the values at these time moments, then we would get the same values as here, right? So here is 0, here is 0, 1, 1, 1, and 0. So the detection would work just the same. And even more so, we have the very same threshold of the half of the energy, which in our case is 50, right? And here also between 40 and 60 is the 50. That is the half of the energy of this signal, which we calculated here somewhere, right? A binary, this row, right? This code line. So basically they are indeed very same. So let me return figure 2 here. And now we need to perform detection. So this is by using command filter. Let us finish this file first, then I will change to convolution and show you that actually that's the same. Now we have made step 2. Now we need to make step 3 to calculate the energy of the signal by sampling output of the filter. So basically we need to read this value, this value, this value, this here, this here, this here, and so on, right? So basically we have to find how many samples are per each symbol. That is what we defined in our beginning of the code when we generated this signal as 0. So we have 200 samples for this signal. Actually, let us calculate the length of this vector so that it automatically updates if we change anything. So this is length of impulse response. Because, well, we use this signal as the impulse response. So if the signal has this length, the impulse response will have the same length, right? And now we can actually change any occurrence of 200 with this L value, so that if we want to change this value at some step here, then we will not have to look through this program and find where we need to change it again. So, and now we need to read each of the L symbols. So basically, let me return again this picture. Basically, here we have L samples. Here we have another L samples, another L samples, and so on. And we need to sample it with a factor of L. So basically here we have something around 2000 points. So we need to read at the position 200, at the position 400, with a step of 200 and further, right? We start with L, go with the step of L, and in the same way proceed up to the end of the signal. So that's how we obtained these indexes, right, which are shown here. So we basically just read out certain values of our filtered output signal, one sample per L values. L is the length of the filter impulse response, right? So after we do that, and we can do that here, detect symbols. First, we calculate symbol energy by sampling the filter output signal, and then we compare. Yes, because actually what we need to do is actually to compare this value with this threshold, if it's more or less than this threshold. And threshold, in our case, for amplitude shift keying is a binary divided by 2, which is calculated already for us. So we are going to put that next here, and we need to call it like as demodulated, like here, right? So that would be a symbol compared to a bit divided by 2. And then we can uncomment this and actually check how we have sent our data and how it was received. So pictures won't change anything because we didn't change pictures, but now in command window we can see transmitted data in the first row and the received data in the second row. As we don't have any noise, it's natural that they completely match. Now we can put on some noise and see how picture is changing. Let us take, for example, 10 decibel signal to noise ratio. The pictures change accordingly, right? So here we can see not so easy to understand signal, but nonetheless, the approach is still the same. We read the value at the end of each symbol, and compare it with a threshold. Right? And that's how detecting is performed. And still, as you can see, there are no errors here. So you need to check multiple signal to noise ratio values in order to actually observe some of the errors. However, please note that here we don't send much data. We only send 10 bits, so you will need to run program many times in order to encounter a single error, or you will need to provide a signal to noise ratio that is really low already. Okay, I have encountered error here. As you can see, I have sent 1 and received 0. That happened at almost last signal, and let's see in the picture how it looks like there. So this is the last signal, and this is the 1 signal. Yes, you can see here that it's actually above 0. This one was below 0, and now here what we have received is actually below 0, below threshold, not 0, but threshold, right? So that's why it was interpreted as 0. However, in fact, there was 1. Now also note that we have very strong noise, and well, the errors just can happen. For that, we are using Hamming coding to correct any errors that happen. Well, also today in our our course project part, we are going to make simulation with much more data. We are going to send millions of data bits in order to check for errors, how many errors we receive, right? So basically this just visualizes the operation of the receiver, and the next part is going to be more effective in computations. So that's for amplitude shift keying. Now I'm going to work on phase shift keying because, well, actually it's almost the same. So I'm going to open phase shift keying, save a copy as fifth lab work, and put, of course, first signal to noise ratio to 100. Now I'm going to copy this entire code here and change any occurrence of amplitude shift keying with a phase shift keying. Also, remember that we need to set threshold to 0 for phase shift keying instead of energy half. And comparison also must be performed this way, less than 0. So as binary is still in binary form, so yes, and that's it, and it should work. So for phase shift keying, it was really fast and easy because receiver is literally the same. The only thing we need to change is this threshold and comparison sign. So let's see if it works. Okay, looks like I have forgotten. Yes, I have forgotten to change BASK to BPSK. And we need to change some more of this here. In fact, label also can be changed. Not defined L. Aha, okay, yes, we did define L in this part of the code, which we didn't change. So that's length of a 0. Right. So now you can see the phase shift keying. And, well, here we are going to compare with the 0. So here, for example, for 1, we compare here. And for second symbol, we will compare at the time moment here, right? So let's see if we received our data correctly. Yes, the data has been received correctly. And now we can put some noise. We need stronger noise in order to encounter error. So let's take, for example, 3 decibel. That is a very noisy channel. But nonetheless, in this particular case, there were no errors. Let's, well, maybe put 1 decibel. We can also actually put 0 as well. It's not a problem. And we encountered a single error. You can see it here. So for phase shift keying, it's literally copy paste and change some values. Now I have promised you to actually try another approach and calculate convolution. So convolution basically is the same thing as this filter command. Basically, filter command relies on this convolution function, but we can use it directly also. So let's, instead of the filtering in this phase shift keying case, let me actually put off the noise as well, are going to use convolution function. In this case, we only need 2 parameters, impulse response and signal. And in fact, it doesn't really matter which is first and which is second. You can put it like this, or you can put it like it's mentioned here. Actually, it's mentioned here exactly the same way. Then, well, let me in fact put them in opposite way so that you can see that actually it works both ways. Because, well, it's in formula of convolution, it's multiplication, right? And as you know, for normal algebra which we use, the multiplication is associative. So meaning that we can exchange these in places. And also, actually, more than that, this would lead to this type of the formula. It's not only changing places, but also changing arguments. So here we would have t minus tau for u, not for h. And that would be the same because, well, the convolution just asks to be to calculate one of the signals in mirror. And it really doesn't matter which exactly signal is going to be mirrored. The only thing that matters is that they must be relatively to each other mirrored. So you can mirror either first signal or second signal, it's irrelevant, right? So let us do this. And well, I'm not going to change anything yet to see if it works already. In fact, it will not work. Well, it works, but it will not draw the last plot because convolution actually calculates, as I have already told you, more samples than filtering, right? So we had at the input 2000 samples and at the output we have 2199 output. So basically we have L-1 more samples than we need. So we need to skip the remaining part somehow, yes, to truncate it in order to, well, match our initial signal and successfully plot it. That is also provided here. How to do that, right? So, in fact, let me copy entire line and put it here. The only thing that we are working now with phase shift keying, right? So this way, now I have truncated the remaining 199 values and will keep only the first 2000 from 1 to 2000, right? And okay, I see we are missing some brackets here. Right, so you can see the very same pictures, moreover, the very same received signals. So it's really up to you to choose. You can, well, in a similar way, use this command for one modulation type, this command for second modulation type, just to, check them both and see how they work. So the last part is frequency shift keying. For frequency shift keying, we are going to need to calculate two correlation integrals. So once again, let us open this file, save a copy of this file as lab5. And, well, everything is done here already. So let's set noise to 0. And now let's copy this code part and put some changes. First of all, let us mention here that L is a length of S0 so that we don't forget it later. Next, let's change all the occurrence of amplitude shift keying to frequency shift keying. Here we are calculating filter. Let it be filter. So this is going to be need a signal 1 because we are going to have a signal 2 as well. Frequency shift keying, frequency shift keying. Actually, we don't need any thresholds now because we are going to compare them in between themselves. Right? And we are going to need 3 plots in this case. So let me copy this one. Plot the first filtered signal. And here we are going to plot the second filter signal. And here is going to be SMF2. So let's similarly calculate the second filtered signal. But first we need to actually calculate the second impulse response. Right? Second impulse response is calculated for S2. First impulse response is calculated for S1. And in fact, we don't have S0 at all. So here we need to put S1. Right? There is no S0 in this case because we have two different frequencies and we generate two signals, S1 and S2. Okay. Similarly, we need energy as for second filtered signal, which is also sampled in the very same way. And then we compare these two energies to each other. Well, I suppose that I didn't miss anything, but if I did, the program will nicely tell me about that. And let's see. Yes, I did miss something. The detection, however, is correct, right? So the problem is only with drawing the plot. I see. It just redrawn the plot at the second position instead of drawing it in third, right? So I need third plot, not the second. So I basically drawn this plot, and then on top of that plot, I draw this plot. And that just removed the second one. So as you can see here, now very similar to correlation receiver, here we have some delta oscillations caused by the initializing of the filter, because, well, filter cannot start exactly working from zeros. Yes, it needs some time. It introduces some time delay in order to accumulate its output value. And, well, basically, we just compare these two signals at each time moment. So here, the first one is greater. Here, the second one is greater. So basically, this represents ones, and this represents 0. So, sorry, if the first is greater, then it's 1. If the second is greater, then it's 0, and so on. And likewise, if we put some noise to our program. Well, let's put 0 signal to noise ratio to attempt to get some errors right. You can see that still it's possible to compare these two signals and make a decision. And well, in this case, we obtain 2 errors in these 10 symbols, right? So at any rate, it's not a viable way to determine error probability. We can calculate that we have 2 errors out of 10 symbols, meaning that estimate of the error probability is 20%. Well, it's not a really viable option because our statistics is too small. We need to send millions of symbols in order to get more reliable statistic. And that's exactly what we are going to do next lecture today on our course project part. And we are going to actually send more data, much more data, in order to capture the error probability more reliably. So for fifth practical exercise, that's it. Hopefully you have seen that actually this works exactly the same as a correlation receiver. And hopefully also, well, you can reproduce these results. Maybe you need some time. I will put the records today at the evening so that you can continue if you started. So that's our fifth practical exercise, and the next week we are going to have our last sixth practical exercise for quadrature amplitude shift keying, where I will show you how can we use a complex analytical signal form to actually speed up the simulation process radically, yes, significantly. But that will be next week. Today, for now, for practical exercise, that is all. Thank you.